Cool. All right. Well, we're back in business. Let me try to wrap this up here. Let's see here. So postulate 5 says if an observable operator A hat has eigenbasis psi n with corresponding eigenvalues lambda n, then the probability that the measurement will yield eigenvalue lambda n of A hat of the system in the normalized space psi of x is this, which is literally equal to that. All right. This is a notation, of course. That's the content of the theorem is equal to that. All right. So let me read his jibber jabber here. This postulate makes several radical assertions. First, it is impossible to predict with absolute certainty the outcome of a measurement that's made on a quantum system in a completely defined state. This is because of the fact that the measurement entails an interaction between the measurement equipment and the measured system. Thus, the prediction of a quantum measurement is of a statistical nature. This is perhaps the most radical feature of the quantum theory of measurement and is completely contrary to the spirit of classical mechanics, which is totally based on the deterministic principle. Second, when a quantum system is in a state psi of x, the value obtained in measurement of the observable operator A hat is a random variable with a probability distribution whose mean value is associated with a large number of measurements in this particular state. This leads to a statistical interpretation of quantum measurements. Third, if two repeated measurements of some observable are performed on a given state, the results of the two measurements will not necessarily be the same, since the operations of the measurement affects the system in general. And in classical mechanics, two or more repeated measurements of a classical observer will always produce identical results. So this postulate makes the most remarkable difference between quantum and classical mechanics because of the special role played by the process of measurement in quantum mechanics. In the theory of quantum measurement, it is important to determine the degree to which the random measurement deviates from the expectation value, the standard deviation, which is a measure of the dispersion around the expectation value, is called the uncertainty. And so the uncertainty is, we've been talking about it all day, right? The uncertainty, well, actually we haven't been talking about it all day. He turned the triangle upside down and gave it a different meaning. Didn't he?
Yeah, it is upside down.
So, rats, I just erased it. What's the right side up triangle? Because didn't we have the, what was it?
The right side up triangle is what we call the root mean square deviation.
Yeah, I'm not.
Also known as.
Is that the, is it, this is driving me nuts. Where's that stupid thing to find?
Page
373. 373. So.
It looks the same to me.
So what the?
Oh yeah, no.
What?
I think they changed it.
What in the Sam Hill's going on here? What? I need an appropriate colloquialism here.
Oh wait, yeah.
I say.
It's like the same thing to me. I can't see it.
I say. I don't see the difference here. What's going on here? Sorry, Audric, what you say?
No, but they said they call the uncertainty triangle A.
Yeah.
Is it del A? No, it's not del. Del's.
Yeah, Del's the one we were using. I would typically call del. So in the previous section we had del A hat quantity squared was the expectation of A hat minus expectation of A hat quantity squared.
Yeah.
Like that. That was the previous section. Current section, section 7.4. Now we have right side up triangle, which I don't have a name for, except for triangle, equal to square root. It's the same thing. It's the same thing. I mean, he, unless I'm missing something, he's just using triangle either way to mean the same. All right, let's, okay. I think let's not sweat over this. I think, it's easy to understand what's going on. There's a certain carelessness in this part of the chapter. We've seen it in the presence of the lowercase a. We've seen it in the lack of the sum in equation 7.78. Let's not worry about it. All right.
Yeah, but they use it all throughout 7.4.
But anyway, the larger point is that this is the uncertainty, right?
Yes, it is.
It's the uncertainty in A hat, right? All right, so, well, it's the uncertainty in the measurement of A hat with respect to the quantum state psi, more accurately, I believe. All right, so, all right, so, my bad. Oh, thank you.
That's nice.
You see it?
Yeah, I'm good.
All right, so I'm gonna. You'll forgive me if I put my triangles upside down where I shouldn't, but I'll try to put my triangles where they're supposed to be. I'm gonna try to track with his triangles as best as I can. Okay, so this is the uncertainty in A, which is the norm of this guy acting on that. It's funny. Is that different? No, it's not. It's not. We had that before as well. Duh. All right, so then he gives this a name. He calls that psi 1. Right? He calls all of this psi 1. Right? All right, fine. Likewise, he talks about triangle B hat equal to the length of psi 2, where psi 2 is going to be the operation of B hat minus the expectation value of B acting on the wave function psi. Since the state vector psi is an element of a Hilbert space, there exists a correlation between the uncertainties. The correlation is the well-known generalized uncertainty principle. All right, so this is, this is a very, very neat result. Sort of the culmination of the things we've talked about today really is right here. So this is the uncertainty principle.
I will assume this is not how Heisenberg actually formulated this.
I don't know. I've never read the original papers by Heisenberg, so I don't know. But any good physicist should, right? Anyway, but here we go. If I'm not a good physicist, A hat and B hat. If A hat and B hat are Hermitian operators, I don't know. He might have. Then
This is not how it was derived in my class.
oh yeah.
Yeah.
But maybe you're thinking of the derivation, for a particular context. Like this is a general one.
You're right.
So you might have derived the Heisenberg uncertainty principle for like position and momentum, whereas this here will simultaneously relate the uncertainties of two operators, right? Greater than 1/2 the absolute value of 1 over I times the expectation of the commutator of the operators. That I is necessary to select the right component, I suppose. I mean, I don't know. It's kind of funny thing to insist on division by I, because you're taking the modulus of that thing. You could just write times I. What would the difference be? I don't know. Honestly, why did you put the I in there at all? If you're taking the modulus of the stupid thing, why are you even bothering writing I?
So why do we have strict? I think it's typo. Yeah, he's using. Isn't it supposed to be greater than or equal to?
Greater than or equal to?
His rest of it.
To be strict.
I mean, just look at the.
Well, he's got a.
Principle for like, okay,
Yeah, he's got greater than or equal to in the proof, and there's no strict there. I think you're right. I think is an equal typo. I'm agreeing. I'm going to go. I think you're right. You said Gaussian wave packet actually achieves the equality. Yeah. So, double check my time here. Uh-oh. Time is just about up. So that's the uncertainty principle. And so the, let me just look at the proof of that right quick. Hopefully I'll be brief. The proof is not long, you know? It's not long. So let's see here. Oof, a little bit dizzy. Proof. So he's like, reminds us the notation, length of psi 1, uncertainty of B, norm of psi 2, where psi 1 and psi 2 were as we defined them a second ago. So if we look at the product of the length of psi 1 and the length of psi 2, by the Cauchy-Schwarz inequality, used in the way we almost never use it, we have the product of the norms is greater than or equal to the modulus of the inner product of psi 1 and psi 2, right? Which is, of course, greater than or equal to the imaginary part of the inner product of psi 1 and psi 2. That's just true. If complex number is always greater than or equal to one of its components. And then this is just a stone cold formula for the imaginary part of a complex inner product. So this is something I would assign my linear algebra class if given the freedom to do such. So your psi 1, psi 2 minus psi 1, psi 2. Yeah, well, that may just be his convention where the inequality refers to all the steps above, not just the one right above it. It could be that. I think that's an equality, actually. I could be wrong. I think that's the equality. And, oh yeah, that is the imaginary part, right, exactly. But then, of course, this is 1 over 2i, and there you've got psi 1, psi 2, minus psi 2, psi 1. And you can start to see how the commutator is going to come up, right? Because psi 1 has got A in it, and psi 2 has got B in it, and they're in an opposite order. That's where the commutator is going to come from, right? So like this is, well, I'm sorry guys, I'm a little bit out of time, but straightforward calculation, greater than or equal to 1/2 absolute value of 1 over I, the commutator of A hat and B hat. It is literally just plugging in this formula and that formula into there and gets that. It's just that. And then, of course, corollary to that, he has the famous uncertainty principles for position momentum, well, for a conjugate variable, you know, a variable and its conjugate momentum, for position and momentum, of course, and for position and velocity as well.
Why is he calling it velocity?
Why doesn't he have time? Like, man, we love the time one in physics so much. Oh, maybe we can't do that yet because that is actually something that's tied to the story of section 7.5, which is on, that's where time enters the scene, right? The Schrodinger equation and all that. We're not there yet. But of course, yes, if we look at this in the context that like A is position and B is momentum, this is Heisenberg's famous uncertainty relation. So fair enough. The energy time uncertainty relation is of a different philosophical nature, I suppose. It's not part of this story. It's part of another story, which hopefully we'll look at next time we meet in this course. I think. I'm hoping.
Is that Wednesday, or are we doing the after?
No, it would be next Monday. Oh, okay. Well, let me turn this off, and then we'll talk about scheduling.